have seen this block diagram of a general pattern recognition system trained using supervised pattern recognition. Specifically in case of speech recognition, we train models at the two levels. One is at the acoustic level, another is the symbolic level. The input to the acoustic model is the features computed from the acoustic signal, speech signal, and the output of the acoustic model are the symbols, that are the phone sequences. Every frame of speech, a speech vector, it tells the probabilities or the likelihoods of the various phones, context independent phones, context dependent phones, and so on. They are symbols. Here there are vectors. So output of the acoustic model is the symbol sequence. One symbol corresponds to every frame of speech. If the speech is 1 second long, it has about 98 frames, about 100 frames, and there will be corresponding 98 symbols with their probabilities. So this symbol sequence is processed by a language model to output a sentence which is a sequence of words. So the language model is language dependent, acoustic model is largely language independent. So the language model takes the sequence of symbols, sequence of phones, for example, context dependent phones, and generates the words. So the language model is primarily a sequence pattern recognition model. Even acoustic model could be a sequence pattern recognition model. It actually is, it does take into account context over large window. HMM was popular in the past because HMM could model a sequence of in features well. Now, a deep neural network seems to do the job better because HMM has several assumptions and many of these assumptions are not reasonable. One assumption is observations of feature vectors are independent. That the first feature vector is not dependent on the second feature vector. Or the next state depends only on the current state, the first order Markovian assumption. And so the deep neural networks seem to have much weaker assumptions, therefore it does seem to be a better model. But how does a deep neural network or a regular neural network manages or models a sequence of symbols? That's what we are going to talk today. And that is done by what is known as a recurrent neural network. A neural network where there is a recurrence occurring again and again. Recurrence is there. This is the block diagram of a recurrent neuron. We are talking of the recurrent neuron. So there is a neuron. Think of the neuron. Neuron takes an input vector at time instant t. It's an x vector multiplied by a w matrix. It gets the it passes through the activation function, and output of this neuron is fed to. This is the output of this neuron at time instant t. Input is x. Input at time t is xt. Output of the neuron is h of t. This is how feed forward neural network were there. So this could be given to another neuron, another neuron, another neuron. There is a layer of neurons, hidden layer, and these feed it to the output neuron or the second hidden layer, and so on. That's how it used to happen. The output of this neuron always was fed to the neurons in the next layer. So the information always flew from this low side to the upper side, next hidden layers, and so on. This is called a feed forward neural network. In contrast, recurrent neural networks have a loop built into the structure. Then the output of the neuron is fed to itself and used at the next time instant. In other words, at time instant t, when an input comes, the output of the neuron not only depends upon the input at time instant t, but also the state of the neuron at previous time instant. So what was the output at the previous time instant of the same neuron is also used in addition to this. So both the inputs are taken and the output is generated. So this is a looping of information. So what does this recurrent neural network actually sort of doing? What we do is, instead of this loop, we unroll it. What we do? Take the time instant t, is t equal to 0, 0 time instant. The input came x0. The neuron does this computation including the activation function, send the output to the next neuron. We call it as h0. And the activity of the neuron is doing the self, means it is stored here. Next time at time instant 1, the test input is vector is x1. The neuron not only uses the x1 but also the state of the memory, let me call it as c0, whatever is at the time instant, to generate the output h1. Therefore h1 depends not only on x1 but also on c at 1 minus 0 previous times. Similarly, the output at time instant h2, that is h2, not only depends upon x2 but also on the cell state at previous times 2 minus 1, that is c1, and c1 depends upon x1 and c0. Therefore the output at time instant 2 not only depends upon x2 but also on the state of the neuron at time instant 1 and time instant 0. In other words, at any point in time, the output ht not only depends upon the input at time instant t but also on the state of the cell at all previous time instances, infinite history. Contrast this with the first order Markovian assumption, which assumes that there is only one state, which has one state, is all that matters. So the recurrent neural network is able to remember effect of past inputs via the state of the cell C. So it is able to model long history. They offer a lot of flexibility. So regular neural network, one input comes, a neuron computes, output goes. So the output depends only on the current input. Here, so one input, one output. Whereas there could be classification. A feature vector comes in case of recurrent neural network, the output of the neuron is fed to itself, the neuron fed to itself, that itself can generate another output. Which means that there could be one input and there could be multiple outputs. What is an example of one input and multiple output? An image is given and you have to describe the image automatically. Neural network which does the image caption. Input is one image, output is sequence of words. One input, several outputs. A recurrent neural network does this job. Next, there could be multiple inputs and one output. A speech is given, somebody has spoken, is he speaking with anger, happiness, joy or sad? Sentiment is one output. Is he happy or not? That's it. Is the customer satisfied or not? This is all that we are interested in. He has talked a lot of things. So many to one, sentiment analysis. This could be spoken language or in the chatting. It could be text. So many to one. You can also have many to many. He said, Mera Bharat Mahan, and the corresponding transcription comes in Assamese or English or Portuguese or whatever language. There could be 3 words here, there could be 7 words here. It doesn't matter, many to many matter. It can even do many to many in different ways, video classification at every frame level and so on. So the recurrent neural networks offer a lot of flexibility in recognizing patterns. Specifically, we are interested in ASR, but let us start to look at recurrent neural networks, how they are sort of trained. A recurrent neural takes input vectors, computes something, outputs something, but the cell state it remembers. Therefore, this is loop there. Generally, we want to predict a vector at some time steps. In our case, it is phone labels, word labels, and yeah, so the output is y. So, the output of the neuron, it is y here, because of the loop, not only depends upon the input at time instant t, output at time instant t not only depends upon the input at time instant t, but it also depends upon the state of this neuron at previous time instant. The state of the neuron, we call it as h of t, h at time instant t minus 1, previous state. H at t minus 1 depends on x of t minus 1 and h of t minus 2 and so on. So this state of the neuron has implicitly captured a history of the state of that neuron. So, new state is function of input and the old state. The function is governed by, in our case, neural networks, the weights of the neural network and the activation functions. So, we can produce a sequence of feature vector x, x1, x2, x3, xt by applying a recurrence formula at every step. Right? Notice that this function is neuron dependent. It doesn't depend upon the time. This function is time independent. Therefore, the weights associated with this neuron are time independent. Let us consider a simple recurrent neural network, because there are other variations of that. Simple one is called vanilla neural network. The state of the neuron consists of a single hidden vector h. It's called hidden vector because it is not directly observable to us. Therefore, that information is called hidden information. It is a vector where lots of information could be stored. For example, in case of a text translation, textual translation from long language to natural language, you can check, you can figure out whether it is what is the part of the speech. Is it the second word in the sentence or third word in the sentence? Position of the word in the sentence. Or how many syllables are there in this word? Is this the second syllable, first syllable, or the last syllable? This kind of information are useful when you do the transformation. Okay. Therefore, this hidden state, the information that it stores, are multiple types. xt is also multiple input, it's a vector, even the hidden state is also a vector. The hidden state at time instant t not only depends upon the input at time instant t, that is xt, but also on the hidden state at previous time instant t minus 1. And it goes through a transformation. The typical transformation that we already seen is the transformation is input into the weight and some activation function. In this particular case, there are two inputs here. So the input at time instant t, xt, gets multiplied by a matrix of vectors. We call these weights as coming from the x and going to the h. Therefore, it is wx at this matrix. Similarly, there is another matrix which multiplies this hidden state vector t minus 1 and we call it as hh, from h to h. That's another weights here. This weighted sum is transformed through activation function tan hyperbolic, generates the state of the cell at time instant t. Remember, this is the state of the cell, not the output. The output goes through one more transformation and this weight, so this is multiplied by a matrix of weights and this is called h, hidden state, to the y, therefore hy. So the y output at time instant t is produced. So you see that there are several transformations that take place here. There is one transformation here, one transformation here. This is a linear, this is a non-linear transformation. There is one more linear transformation here and output y at time instant t depends upon all these factors. So we keep getting used to this concept of a weight matrix multiplying a vector and then going through a activation function. This becomes very recurrently occurring theme that we will see. Let us see the application of such a new recurrent neural network in the case of a character level language model. What does the character level language model do? It is trained with the large number of, let's say, English text, Roman's characters A to Z, but English language. If it is trained, next time some input comes, it will be able to predict what would be the next word, next letter, and so on. This is character level language model, therefore it predicts the next character given the previous few characters. We take the simple vocabulary H, E, L, O. There are only 4 characters in the language, and example training sequence is hello. Fine. So let's feed it. There are only 4 inputs that are possible. It's a discrete feature vector. Since there are only 4 inputs, we can encode it using the one-hot vector. So the character is one of the 4. Since it is the first character, this input is first position is 1, all others are 0. Only one of these values will be 1 and all others will be 0. That's why it's called one-hot vector. If the input is H, it is the first one, therefore 1, 0, 0, 0. If the input is E, it is the second, therefore second one is on, others are off. And whenever L is there, it will be indicated by this 4-bit sequence of 4 bits, where the third bit is active. When it is O, the fourth bit should be active, and it is O. But it is L again, therefore this will be failed. So the input is a sequence of 4 bits. It's a one-hot vector. Let's see what happens. Input is given H. Let's say the hidden vector generates some hidden state which is a 3-dimensional quantity. And during the training, we train using this. Initially it will have arbitrary weights, and it gets, as training progresses, the weights get changed. So you see that there is a weight matrix associated with the state of the cell at the previous time instant to the state of the neuron at the hidden state at the next time instant. Whereas the weight matrix WXH is associated with the information flowing from the X input feature vector to compute the hidden state of the neuron. So you see the 2 weight matrices here, and they appear here in computing the hidden state at time instant t. We know after H it should generate E. After E it should generate L. After L it should generate L, the next character. This is the desired output or the target output. And output layer has produced these numbers. What we need is the output layer should produce this number because E correspondingly, which means that second one should be maximum 1, all others should be 0. That is the desired. Computed output is here, so we know the error, so we can train the neural network. So you see here, initially E was supposed to be the second one, this is higher, alright, this third one should be higher. There is a problem here, it's not trained correctly, so with time it will these outputs because the weights get trained. Okay. So we are training the system. Once we give large amount of data like this, a large text, English text, the phoneme, letter bigram, letter trigram, letter n-grams get encoded here. I am not saying letter bigram or trigram because the memory of the neuron can store infinite memory in principle. Therefore, in principle it can store n-gram information. Although that the history becomes a bit weak. So let's say you train a neural network to predict the next character. If you give this as input, after training with some amount of data, you get this output. You see that they are all nonsense. You also see that there are spaces in between, there are some commas coming in. So it knows that these characters do occur, but it is not producing output. You train it with a little more data, once in a while you will see something like vowels and consonants are coming in alternate order. I is a word on itself. There is a word, regular word called on, and so on. You start training with more data, it starts printing more and more regular English words. With a lot more data, it produces what looks like grammatically correct sentences sometimes, but maybe semantically it is meaningless. But it is possible to predict the next letter. So you see here that the recurrent neural network is able to train a language model. So we can use the recurrent neural network to train language model for automatic speech recognition also. You can, in fact, even the acoustic vector sequence is not independent vectors. They are all related because it's generated by a physical system. The feature vectors of the adjacent frames are correlated, and a recurrent neural network is able to handle this much better. Therefore, they are used in automatic speech recognition. Here is another example where some code, Linux C code, was used to train, and it generated some C code. It looks like a C code, but because it looks like static void, some function name, some struct, some pointers, curly brackets, and something like this, and so on. But if you look at it carefully, it is not correct. But it produces something that resembles a valid C program. So neural networks can model a language model, a sequential model. But this has some problems. This is a code of such a Python code of neural network with RNN. The gradient descent algorithm involves weight updation. Weight updation involves minus eta into df by dw. If this gradient, the derivative, if it is much larger than 1, multiplication of very many large numbers will lead to a much larger number, and this gradient can go to infinity, very large. Such a situation is called gradient explosion. So you need to do some controlling. If the gradient goes beyond certain point, you clip it. Do not let it go beyond certain value. On the other hand, the gradient could be extremely small, 0.1, and many such gradient derivatives are multiplied together, it becomes extremely small, or the gradient can vanish. So you need to take care of this vanishing gradient problem also. This is typically taken care with the long short-term memory neural networks, which we'll talk next time. So there are issues with the neural network, but it can be handled. Summary: recurrent neural networks allow a lot of flexibility in architecture designs. The simple neural networks do not work as well, so we need some changes to be done, like here. We can use gated recurrent unit to improve performance, and the problem of vanishing gradient or exploding gradient is typically handled using long short-term memory. How do the recurrent deep neural networks work with the acoustic model? Well, here is an example of the deep neural network. But you see here, there is an extra arc that has come here. The same neuron, the neuron not only takes the input from the previous neuron, but also its previous state. So this is a recurrent neural network coming into the acoustic model. You can have deep recurrent neural networks. There are multiple hidden layers, and the hidden layer, the neuron in a hidden layer can take its previous state as the input in addition to the input feature vector to predict the output, and there could be multiple hidden layers of this type. Deep neural networks, recurrent neural networks have been used successfully in speech recognition, and they have some limitations, and these limitations are overcome by some modifications, and even a better version of it is called long short term memory, LSTM, which we will talk in the next class.